very much trained in AI and has developed what has trained AI. I had it in the beginning. It was it's a pleasure to have them with us, to have industry in this discussion with us. Thank you all for welcoming David Hall to the stand. Thank you, David.
Hi, everybody. You probably don't recognize me or know me because I am new both to the ocean AI sector and to this continent. I recently relocated from the United States to Germany. What I am not new to is, is artificial intelligence and its applications to weather and climate. As a matter of fact, I was the first person that NVIDIA hired in this field, so I've been doing this for 8.5 years now, long before it became popular with most people. So what I've seen in that amount of time is an amazing amount of transformation, and NVIDIA's efforts in this area have gone basically from zero to a very large collection of skillful models. But we've mostly been focused on the atmosphere up till now, weather and its extensions. But now that we're heading towards seasonal to subseasonal and climate and things like that, the ocean is becoming a very important focus for us. And that's why I'm here today. Good, it worked. So we originally set out to build this incredibly ambitious thing called Earth-2, a digital twin of the Earth. It was announced as sort of a surprise to the few of us who were working in this. Our CEO got up on stage and said, we're going to make a digital twin of the Earth. And there were just a few of us, and we were like, oh. We didn't know that. It was exciting, though, and we set out to cover all spatial scales and all temporal scales, but clearly not all at once. We had to start somewhere, and we started with weather, with ForecastNet 1. Oops. So the first model was ForecastNet 1, and it sort of kicked off this amazing gold rush in terms of AI weather forecasting, because it was so incredibly successful. It was a very simple model trained on the ERA5 reanalysis data set, but it was accurate and incredibly fast, like 1,000 to 10,000 times as fast as the traditional approach for simulating this thing. Next thing you know, everybody's training these AI weather models, and there's a lot of excitement around it, and that's nothing but great as far as we're concerned. From there, we moved in lots of different directions. We wanted to go to higher resolution, so we created a downscaling model called CoreDiff. And then when that was successful, we moved on and said, okay, let's do regional forecasting. So we created Stormcast, trained from the high-resolution rapid refresh model. We've recently moved into StormScope, which is a direct observation to prediction model, where you take the satellite observations and directly predict what's going to happen next, so skipping the initialization and data analysis stages entirely. We have our own AI approaches to data assimilation. Am I skipping any models? Yes, climate in a bottle. It's where we take a giant petabyte scale model and compress it down to something small that you can move around and then regenerate those states. And then there's DELISIM, which is our most recent thing. It's a collaboration with the University of Washington, where we're trying to build a coupled climate model. So as you can see, conspicuously absent from this are seasonal to subseasonal forecast timescales and ocean simulations. All the things that we build, each of those is a very powerful and useful and valuable model, and they're all given away for free. We do not do forecasts. We do not sell any services. Everything at this level is for free. The hardware is not free, however. So we encourage you to do everything you can, and we're here to support you in that. And you can download all these models and try them out with our Earth-2 Studio tool, fine-tune them with our Physics Nemo tool. Apparently, my thing's on automatic timing stepping, but that's fine. So the next major frontier for us is the ocean. So weather's fast, and the Earth system is bigger than just the weather, and in order to get the next timescales, we need to be able to include the ocean if we want to do anything beyond what we've done so far. The ocean, from what I understand, is harder. Like I said, I'm kind of new here. It's got 3D complexity, so is the atmosphere, but there's a lot of bathymetry to deal with. There's a lot of different physics at the different levels. But I think the biggest challenge is that the amount of observational data is limited, right? So the atmosphere you can see through, you can basically see everything. There's lots of sensors sampling it, but the interior of the ocean is pretty hard to see. So that's obviously an interesting challenge. Mostly the models are based upon other simulations, and I think that's where people have been building mostly. The ocean also has long memory, so it can drift over long periods of time if you're not careful and accurate. So the main effort we have going in this area is a close collaboration with Dale Duran's group at the University of Washington, where he's building the deep learning Earth system model, DELISIM, which is a coupled climate model. He started out with a version 1 model, which was a coupled atmosphere with just a sea surface temperature field representing the ocean. The basic approach that he was trying to get was just to show that this was stable and that it produced outputs that made sense. This model runs happily for 1,000 years of simulated time. It's stable the entire time without blowing up, and it does some nice things. It automatically produces tropical cyclones spontaneously without having been trained to do so. So that's pretty great, and we're happy with those successes. And go back. So the version 2 model, which he's working on now, it takes some additional steps. It adds some additional components. We now have a stratospheric component to the atmosphere. And we have a 3D ocean, although it's not the full depth. It's just the first, I think, 300 meters. And they've also added sea ice. So we're taking steps towards a more complete model. And from what I understand, it's working quite well. So one of the components of this model is a dedicated ocean called Deep Learning Earth System Ocean. And here you can see some results of what happens to it when it's forced by the atmosphere, the Era 5 reanalysis as an atmosphere proxy. And you can see that it produces many different ensemble members that do a good job of capturing the El Nino Southern Oscillation. Well, at least they capture the timing and onset very well, even across the springtime barrier. They do not yet capture the amplitude completely correctly, so that's something that they're still working on. But it's nice to see that the ensemble model is working well. It also does a good job capturing sea ice. This is a component that's been added to it recently. These results are basically brand new, not yet published. And we can see that it produces realistic sea ice extent, both for the Arctic and Antarctic, especially for the Antarctic region. The annual mean is particularly accurate. So it's nice that this model is producing both ensemble ENSO predictions and accurate sea ice predictions pretty much right out of the box. The other collaboration we have in this area is with the team that built Samudra, the full depth ocean model. Samudra simulates the full depth. We did not build that model ourselves, but we did work very closely with them to accelerate it, to make that model 150 times faster than the original. It is trained on 65 years of output from GFDL's OM4 ocean model. Yeah, and so it's a very nice model. It's got the full 3D ocean. It predicts ENSO well. It predicts the structure well. It's a very nice proof of concept that this can be done and can be done well. We also are somewhat represented in their work on ACE, where they coupled the Samudra model to an atmospheric model and an ice model together and showed that it has very nice properties. We didn't actually work directly on this, but they did build it on top of our SFNO structure that was built using forecast. So the atmosphere model is essentially built on top of ours, and the ocean model is Samudra, and you couple them together. And it proves that you can couple atmosphere, ocean, and ice together and get a very, very good set of results. So as you've seen in this session, there are a number of ocean models now in the AI space. Basically, all of these are new to me, honestly. And I'm excited to see that there's so much work already being done in this area and so much successful work being done in this area. Obviously, people are approaching this from many different directions, and it's converging fast and converging well. So I expect to see some cool results out of NVIDIA's efforts as well in the near future. So open challenges that remain is that many of the ocean models remain deterministic. And as we discovered in the atmosphere a long time ago, if you try and predict a chaotic system with a deterministic model, you get fuzzy results because it ends up trending toward the mean field because it can't predict one or the other. It has to predict the best it can, which is pretty much the average of the set. So moving towards ensemble methods is a good way to go, and we're happy that the DELISIM model handles that well. The other thing that we have to deal with, of course, is building trust in these systems. In the atmosphere side, we're doing pretty well. ECMWF built their own AIFS model, and they ran it for a long time and saw that it had a lot of great skill. And so they operationalized that and used them side by side with their traditional model. I think the same thing needs to be done with the ocean to build up trust, and I'm sure that will happen in short order. So the path forward looks pretty bright. DELISIM is going toward a fully coupled system. The ocean is producing very good results. We have the nice Edito system here to display things that I've recently learned about. Ocean Bench is already in place to characterize these models. And the open tools that NVIDIA produces, like Earth 2 Studio, is there to lower the barrier to entry for people to use all the open source models and in a free and transparent way. So one last point before I conclude. Beyond what we're doing with training AI models in the sort of traditional sense, where you input data and you input the inputs and input the outputs and get the model to do what you want it to, there's a whole other branch of artificial intelligence that's going on right now, which is large language models. With the large language models, you can do AI coding, and you can do create independent agents. And it's a very large and powerful set of AI tools in itself. And even at NVIDIA, at least in the Earth 2 system, we are underutilizing these. And so I set out to learn how to use these as effectively as possible. So I went to build some interesting tools to master these tools, and so I can teach other people how to use them. So I built this thing that you're seeing here. I call it World Scope. It's basically a 3D globe that can do many different things. And I built it with the help of Claude Code. And I'll be out there showing it off at one of these podium things during the coffee break. So if you'd like to see a bit about what I did there, please come talk to me. Thank you.
Thank you very much, David. And I have a question for you that I'm going to let you answer if you wish during the roundtable, so we don't take too much time left on the roundtable. But I'm going to ask you now just so we respect the symmetry and you get your question just like everybody else. Absolutely. Okay. You came from Germany as well. Welcome to Europe, by the way. And so it is because you know so much about the history of integrating AI into the economy, to say things in a very large way, if I might say so. What would you say are the little risks to avoid in the next few years, as you've already witnessed kind of a gold rush, as you said, on these new technologies? And so what risks to avoid in how we use it and how we kind of implement it into more and more practices? So that's the question I have for you. You can choose to integrate, an answer to that question during the roundtable. And you can stay on stage. I'm going to be efficient, and I'm going to, you can have a seat, please.